This is TMUA question of the day, day 19 hints with stopmaths.com and Tobin Payne. So our first question today are A level plus. So it's a pair of simultaneous equations and we're looking for a value of y. It's non-standard, hence the A level plus, because you've got a quartic and you've got a quadratic. Now, you don't necessarily, with these kind of TMUA questions, these harder questions on simultaneous equations, want to just go for eliminating a variable. So you don't necessarily want to say, well, let's make y squared the subject of the second equation and then see what happens there. So with this sort of thing, always look to see if there are any clever factorizations you can do, even if you don't have an equals 0. And hopefully you can see that this is the difference two squares. Once you've got that, you will notice, and I'll just do that bit. So we've got x squared plus y squared, x squared minus y squared equals 2009. And we know x squared plus y squared equals 49. Now, if the examiner's been kind, which they almost certainly have, to a degree at least, 49 will be a factor of 2009, and then you've got something that's a bit more standard, because you'll then have x squared minus y squared equals 2009 over 41, whatever that is. You've then got a new version of essentially one of the equations, so you can then solve that simultaneously. So do look out for clever little factor. I say clever, it's not. Look out for factorizations ultimately when you've got simultaneous equations. Now, this is interesting because this is essentially saying we need n divided by 100 minus n to be an integer, which means we need n to be a multiple of 100 minus n. Now, you could probably figure out a few values that would definitely work. For example, if n was 50, we'd have 50 over 50. If n was 75, we'd have 75 over 25. If n was 80, we'd have 80 over 20. So what's important here as well is the choice of words. They've used the word integer. They haven't said positive integer. They've just said integer, and that's going to be important. Now, you could go down the Diophantine equation route. You could say n over 100 minus n equals x, where x is an integer. You could then maybe try and make n the subject. But it's always nice if you've got the ratio of two functions like this, two linear functions especially, you can say that n over 100 minus n is equivalent to, and we want to make the numerator a multiple of the denominator, so we're just going to go for 100 minus n, and then to make sure that that is still the same as the numerator there, we're going to do 100 minus that. So you might consider this a little unusual, but it's a bit like partial fractions in a way. We're just writing it in a way that's then going to end up as 100 over 100 minus n minus 1. And that's easier because if that's going to be contained within the integers, then ultimately that means 100 over 100 minus n is also contained within the integers. And this time, because the numerator is a constant, it's easier to deal with this. But just remember that you can have negative integers as well. Our third question, our geometry question. In A-level maths, there are a couple of circle theorems you need to know. And one of them is about angles in a semicircle. Now, if an angle is acute, that means it's less than 90 degrees. So think to yourself, how could I draw a loci of points such that P is on this loci, then P would be equal to 90 degrees, and think circle theorems. Once you've got that loci of points, you're essentially saying you want P to be inside that loci, i.e. closer to RQ. Now, this one is our logic question for say. This is a hard question. There's no two ways about it. And you've got to be really, really careful and systematic, like any of these logic questions. Ultimately, what the first challenge you're going to face is recognizing how the vertices meet. So these 5 vertices, for example, are all going to meet. And we also could say that these 5 triangles here meet at this vertex. So we need to try and organize our thoughts a bit here. So we could say, well, let's label our triangles. So we've got top row, bottom row, middle row. The top row, we've got T1, T2, T3, T4, T5. The middle row, obviously, we've got up to M1, M2, up to M10. And then we've got our B1, B2. Now, this is going to come down to elimination. It's like a really horrible Sudoku. So you don't have a 5 anywhere. You do have a 1. You know that if I think about where a 1 can't go, well, a 1 cannot go there, and a 1 cannot go there in the top row. But we know one of the top row triangles needs to be a 1. That means a 1 is either here or here. So if we think of the top row, we can say the number 1 has to be at either the second or the third triangle. Well, the number 2's already present in the top row, so it's definitely going to be number 2. We can cross off, and we're just slowly and systematically. But you've got to choose a method as well. Do you want to think, where does the 1 have to be, or do you want to think what can't go per triangle? So do you want to focus on an individual triangle, or do you want to focus on the numbers? When you're on the bottom row again, you can think, these 5 points are going to meet, so you can say stuff, well, none of these can be a 4. So if you're thinking about where the 4 is, the 4 at, say, this vertex is going to be either here or here. So either that's a 4 or that's a 4. So just slowly and carefully eliminate your options, but choose a method. Are you focused on vertices? Are you focused on triangles? Are you focused on numbers? Whatever it is, stick with it. Don't jump about all over the place, otherwise you'll miss the correct option.